So now we want to find out how far it'll go and how high it'll go. We want to turn time into a distance that I can measure with meter sticks. So first, to find out how far it'll go, we just plug it into the x equation. And we've already plugged in the horizontal velocity because we're dealing with side to side. And we just plug in the larger number for time, because that we're finding out how far it'll go at the end when it hits the ground. And then you get that it'll go back 4.5 meters, which I attempted to measure with tables. Then to find out how high it'll go, it gets a little trickier, because it'll be at its highest at the peak of the parabola, which is the exact center. And the center is between the x-intercepts, which means between both of them, you can't just divide the bigger one by 2, because we have this weird negative time. So we actually have to combine them, ignoring the negative, to get 0.708, and then divide that by 2 to get half the parabola, and then plug that number in. And when you've done the math, it comes to about 0.58 meters high, which Jen will be holding up later, since we don't have duct tape. Now we can start to graph our path before we've ever actually launched it. We know that at 0 seconds, it will have gone no distance, and it will be 26 centimeters up, 0.26 meters, because it hasn't been launched yet. It's just here. Then at an unknown distance, but half of the parabola, it will be at 0.58 meters in the air. And at 0.623 seconds, about, it will have gone 4.5 meters and will hit the ground again. So we want to find n to get that parabola. And n is half the distance between the x-intercepts, which means we have to deal with the weird negative time again. So we have to plug that weird negative time into the x equation to get a weird negative distance, this imaginary whatever distance this part of the parabola is. And then we add that negative number to 4.5, which is the positive distance we're actually dealing with, and then divide that by 2 to get halfway. It took me a while to figure that out. And so then we get it's 1.9, and we can graph it. Graph. And so we get this beautiful path in which here's the catapult, which will be put over there. Here will be the ring when Jen's holding it up, and there's our little box thing. And so, just to put things into perspective, here's a path without gravity. We'll just keep flying on forever, but because we have gravity, it curves and comes back down to the ground. So let's fire it up, Jen.
Alright. So how am I doing it and from where? Yeah.
You might want to not get hit on level.
Maybe.
Don't like it. Yeah, like
Also difficult to aim this, but hopefully it's aimed. And I'm going to have to run after this marble because I can't lose it. I've already chased it down the trash can. It's not cool.
With frog nuts in it.
Yeah, that was fun. Alright. It hit the ring, but it didn't go into the basket. So, what happened? Well, yep, I knew it was actually going to do that. I knew it wasn't going to be perfect. Why? Because I didn't count with air resistance, but with something this small and that little of a distance, it shouldn't have actually mattered that much, and it went farther, not as far. So the real problem of error is calculating that initial velocity, because if you look at all my equations, they all go back to velocity. And calculating velocity when the ball's in the air for under a second is kind of difficult. And to show you this, I'll walk you through all my errors, all my past attempts that did not work. First, I tried to do it scientifically, get science more in there. And so I used a spring scale, an electronic spring scale, to figure out the force of the spring, and I multiplied that by distance to get work, and then I plugged work into the potential energy equation, and then I assumed that all the energy would then be transferred into kinetic energy, and then I solved backwards for velocity. That did not work. All my numbers were way too huge. At first I thought I was dealing in decimeters because I was getting really big numbers. But that's because 3, 9 to 12, and everywhere in between, and it would not stop, so I had no idea what number it was actually at. I didn't account for any friction or any loss of energy in the transfer, which is probably a big part of that. I assumed that when you let go of the spring, all the energy would then be transferred into the ball moving through the air, and that's not going to happen in real life. And I also had not grasped the math yet, so that's a huge thing of why it didn't work. A second failed attempt, I was trying to be sneaky and calculate backwards. So first we just kept launching the marble until it finally did go through the ring, and then I tried to calculate backwards to get velocity from there. That didn't work because I got it through the ring, but the ring was not halfway in the path. The ring was way over here when it still went that far. And I have no idea why. I had really weird equations that I didn't know why worked. And so that happened because we were working backwards from the wrong starting point. We'd been firing it over and over again to get it through the ring, but we never stopped to make sure that the ring was halfway in the path. So then I got that weird number, and I was still using I still didn't understand the equations, which is again why that wouldn't have worked. I didn't realize that you had to get the vertical and horizontal velocity. That didn't exist in my head. And my last failed attempt was what you saw. It was close, hit the ring, but it didn't go that far, and it went farther than the basket. And that's because, or what I did was, to get this velocity, I put it horizontally, and we launched it, and we tried to time at what point it was launched to the ground, and then measure that distance. The problem with that is humans have really slow reaction time compared to the speed that this marble moves through the air. When it was going up into the air and down, it's in the air for under a second, and when it's launched horizontally, it's in the air for about a quarter of a second, and that's really difficult to time correctly with a stopwatch. We were getting numbers that were like 0.25 to 0.55, and that's a big difference when that's all you're dealing with. And also, when the marble hits the ground, it doesn't stop, it keeps going. And so trying to figure out where it hit the ground and measure to that point was kind of impossible when it kept flying down the hallway, and we were focusing on where it went so I could go and run after it, because I can't lose this. Also, conditions vary. I could sit here and keep launching that marble launcher without moving anything, and one of the times it would go through the ring, another time it would go in the box, and another time it would completely miss everything. Because every time I launch it, depending on how I pull it back and just depending on the spring and the differences in the environment, it's going to travel at different velocities. And so it's impossible to get a perfect predicted path. But as you saw, it was the closest I came. It tapped the side of the loop, which probably if I moved a little bit sideways, it might have gone through. It didn't land in the box though. So in conclusion, my project was kind of doomed to fail if I was aiming for a perfect path.
It's okay,
But it was still a success because I got really close. And so I did more or less what I set out to do. I predicted the path, and I did get close, and it's impossible to actually get a perfect path.